And let's look at the sample test for Chapter 3. The price of gasoline has tripled over the last 10 years, decade. Dollar per gallon to $3 per gallon. That's the tripling. Whereas diesel went from $1 per gallon to $3.50 per gallon. Use the above information to write one true statement as percentage using percentage as a fraction. So let's write one true statement. So let's just say, losing the gas, it used to be $1 and now it's 3. So 1 to 3. So gas used to be 1/3. So in percentage, it says use percentage. So on 1 divided by 3 is 33% of what it is now. So the reference of is what it is now, $3, and it used to be $1. Now you could do 1 over 350 for the diesel. That's a possibility for A. B, use the information above, write one true statement using percentage as change. Okay, so let's just use the gas again. It went from $1 to $3, but we're doing percentage. So the difference, the absolute difference, is $2. And it started at $1. So the change is $2 over the decade. And so the change is 1 divided by 2, or 2 divided by 1, 2 divided by 1, which is 2 times 100, is 200% more. This is 2 times 100, 200% more. 100% of what it was, the $1, plus 200% of the $100 more. So it's 200. Gas is 200% more than what it was 10 years ago. Use the information to write one true statement using percentage as a comparison. Okay. Now let's use the diesel. So the difference between the gas and the diesel is 50 cents. And more than what? Diesel is 50% more than gas. So we're comparing it to gas. So we put the $3 under it so that we can say this is how much more diesel is than was the gas. So change that to percent, 0.5 divided by 3.00 times 100, and 16.67, 16 and 2/3, 16.7. Diesel is 16.7% more than gas currently or now. So we're comparing it, so it's more than gas, so the gas has to go, the price goes in the denominator, and the difference goes in the numerator, and it's plus 50. Now you could go minus 50 and put 350 here and say gas is whatever 50 divided by 350 times 100, and you could say gas is 14.28% less than diesel currently or now. So that's D. No, that's C. A, B, C, D. Use the information to write one true statement about the absolute change. So we could say gas increased by $2 over the decade, or diesel increased by $2.50 over the decade. I'll just do gas increased by $2 over the decade. See, absolute change just says how much difference are they? Don't do a percentage. Use the information above, that's D. Use the information above to write one true statement using percentage points. Okay. Let's see. So I got to think about that one. I'm going to move on because we didn't do that much. This was an old test and we didn't spend as much time on percentage points. So I'm going to leave that one off of here. Don't worry about that one. Okay, determine the percentage that would belong in the blank. Sue is 12% taller than Isabel. So Isabel's some height. And Sue is 12% taller than Isabel. So Isabel's the reference. So this is Isabel's height. And Sue is 12% more. So if I divide this into 100 pieces, 50, 75, 100, 25, 25, 50, 75, 100, 12 would be, that's 25, 50, 12 is something like this. So that 12 would go here. So here's 100% and 12 more. So Sue is 112%, or 1.12 times, but 112% of Isabel's height. Jorge got a raise of 120% of his current salary. He got of his current, 120% of his current. So you would take his current and multiply it by 120% in decimal would be 1.2. So it would be 1 of it and 0.2 more. So if he got 0.2 more than his original salary, 100% of it plus 20% more, his raise was 20% raise. Harold's net worth has decreased by 15% in the economic downturn. So his net worth now is what percent of his original wealth? So his original worth, and it went down by 15%, so you got to divide this into 100 pieces. 25, 50, 75, 100. 15 would be somewhere here. So this amount is taken off, the 15%. Well, how much is left? So his net worth is what percent of the whole thing here? Well, 15 is off. 85% is what's left. Dimitri makes 30% more than Chaz. So Chaz makes what percent of what Dimitri makes? So if this is Chaz, we call that 100%, then Dimitri makes 30% more of this. So 50, 25, 30% would be something like this. More. So Dimitri makes, this is what Chaz makes. And this is what Dimitri makes. Okay. So Chaz makes a smaller portion of Dimitri. So if Chaz is this, and Dimitri is this, which would be 130%. So Chaz is 100 out of the 130. So what's that work out to be? 100 divided by 130 times 100 to make it a percent, 77%. Took 100 divided by 130, then make it a percent. Okay? Your dinner bill is $52.90. You leave $70 tip, or $70. Pay for the meal. Standard tip amount is 20%. How many points higher or lower? So how many percentage points higher or lower is your tip? So if you paid 70 and normally it's 50 and the bill is $52.90, how much was the tip? So you would take the 70 minus the $52.90, and that is a tip of $17.10. So your tip was what percent of the bill? It's always of the bill that you calculate your tip towards. So 17.10, $17.10 divided by the 52.90 times 100. You tipped them 32.3%. But the normal tip is 20%. So how many percentage points higher is this than that? So your tip was higher by, 20% from 32%, 12.3 percentage points higher. You gave a bigger tip than was needed. Okay, you were so generous. All right, the next one. Monday morning, your stock was worth this amount. It decreased by this by the end of the day. Tuesday was better and it rose by this amount. What is the price Tuesday morning? So Monday morning it's here. It decreased by this by the end of the day. So Tuesday it was at that same price because it doesn't change overnight. So it decreased by that amount. So how much is left if it goes down by 5.12? Well, was 100%. It decreases by 5.12%, so it's only 94.88% left. So we'll take that times the price, 21.47. Yep. Now, what did I do wrong? Oh, I forgot to change that back into decimal. So I want to do 21.47 times 0.9488 for 94%. So it's now worth, on Tuesday morning, let's do it here. We take 100% minus the amount it went down, 5.87, which turns out to 5.12. 5.12. I'm getting the wrong numbers. Okay, that was this one. So that's 94.8%, 88% left. So I take the amount it was, $21.47 times the 0.9488 decimal form of 94.88%, and we get the price is now of that stock, it's worth $20.37 approximately. Okay? What was the absolute change from Monday to Tuesday? Oh, it went from 21.47 to 20.37. The difference between those, if you subtract them, is $1.10. Absolute is just the difference. What was the relative change from to Tuesday evening? Ooh, we only did Tuesday morning. So I got to do more here. I got to take it now and do the next. So it went up by 5.87. So now it's going to be 105.87 that we have to multiply, because it's going up by 100% and 5% more. But I would change that to a decimal, so we're really going to multiply by 1.0587. I'll keep all the digits here and take it times, all that times 1.0587. It's now $21.57 on Tuesday evening. So from Monday it went down, and then Tuesday it went back up. And what's the absolute change? So it started at 21.47, ended at 21.57. So the absolute change is plus 0.10 or 10 cents, 10 hundredths of a dollar. What was the relative change from Monday morning to Tuesday evening? Well, that would be the 10 cents, the absolute change, divided by the starting amount. Starting amount was 21.47. These are both dollars, so they cancel. Then we take it times 100 to make it percent, and we get 0.10 divided by 21.47 times 100, and we get the relative change of 0.47 or 66%, something like that. That's approximately there. So the idea, you do the difference divided by the reference value for the relative change, changing it to percent. And the difference is the absolute change. Okay, so 3 parts to this one. First part was, what was it after the first day? Then how much did it change from Monday to Tuesday evening? So it went to there, then it went back up to here. So from the first day to the end of the second day, it went up plus 10 cents. That's the absolute change divided by the starting amount. Change it to a percent, and you get the relative change. Okay, page 2. There's approximately 2.2 million marriages in the U.S. per year. How many marriages are there on average per hour? So 2.2 million, that's 2 million, comma, instead of decimal, 200, comma, 000, million per year. And we want to know per hour. So we've got to change years into days. So we want year to cancel. And there's 365 days. And then we got to get it to hours. So we got to multiply by 1 day is 24 hours. Days cancel, years cancel. And so we're going to get 2,200,000 times 1 times 1. So that's our numerator. Divided by, in the denominator, we have 1 times 365 times 24. I need to put parentheses around it. I need to divide by that and then divide by that, but I'll just do it in parentheses so I get them both. 365 times 24. And that means there's 251 marriages per hour. Well, a lot of people getting married. And consequently, there's a lot of people getting divorced. Hopefully, not as many, less. In 2007, Procter & Gamble spent $52 billion on advertising. If a stack of $10 bills is 1 millimeter, how high would $52 billion in $1 bills be in kilometers? Oh my goodness. 5.2 billion. 5.2 billion. So these are the millions. So these are the thousands. And these are the ones, hundreds, tens, and ones. And 10 of them. So this is dollars. And it takes $10 to make 1 millimeter. So the dollars cancel. And then we've got to do, so that'd be a lot of millimeters. And then we got to change millimeters to meters. So let's see, 1,000 millimeters, because they're little tiny things, makes 1 meter. And then we got to go to kilometers. And so 1,000 meters makes 1 kilometer. So the meters cancel, the millimeters cancel, and the dollars are canceled. And so we got 5,200,000,000 is the numerator, divided by parenthesis. In the denominator, we have $10 for 1 millimeter times 1,000 millimeters make a meter times 1,000 meters make a kilometer. So it's 520 kilometers. Now, if you wanted to know, if you divide that by 1.6, it would go 325 miles. Procter & Gamble made 5.2 billion, spent that much on advertising. So if it was in $1 bills, stacked up, laid down, it would go 325 miles. They would be stacked, a stack laying on its side from here to Spokane. That's a long way. How many significant digits for each of these? And then what is the implied error in absolute and in percentage? So 2.315 significant figures, absolute error, and percentage error. So significant digits, there's no pushers, 1, 2, 3, 4. Absolute error, that would be 0.000 the next place, 000 the next place, 5. Could be plus or minus. So what's the percentage error? This divided by the original number changed to percent. So 2.315 divided by, backwards, 0.0005 divided by 2.315 times 100. Percentage error relative is 0.02%. 6.0100. Here's the decimal. There's whole non-zero numbers on either side, so that zero counts. These are not pushers, they're added on the end, so they must count. So there's 1, 2, 3, 4, 5. Absolute error, not this place, not this place, not this place, not this, that one. 1, 2, 3, 4 zeros, 5. 0.00005. And the percent error would be 0.00005 divided by 6.0100 times 100. And so it's got to divide by 10 4 times. So if I put the 8, the decimal on that was here. So if I move it 4 times, dividing it, making it smaller. 1, 2, 3, 4. Really small percentage, and it is percentage because I multiplied by 100. Next one, 0.0002102. These are pushing it over. There's no number over here, just 0. So these are pushers, so don't count them. That's between numbers, so we keep that 0, so there's 3 of them. So it should be less percentage here, but the absolute error is pretty big. 0.0000005. 6 zeros. 5. 0.1234565 divided by 0.000102 times 100. Percentage error is 0.49%. It's not 49%, it's 0.49 because I multiplied by 100 already to make it percentage. Next one. 4.09 times 10. I missed one. 30500. Those are pushers. So 1, 2, 3 of them. So I should get about the same kind of percentage as that, near it. 1, 2, 3, that's the one that's iffy. So that's 0.50 point. Now this looks like a large absolute error, but really when this is a larger number, so 50 divided by 30500 times 100.16%. Less error, but still reasonably close to that for 3 significant digits. Next one, when it's in scientific notation, there is 3 of them showing. The number is 4, then I got to multiply by 10 11 times. So moving it over to there is 1, moving to there is 2. That's 2 of the 11, so there's 9 more. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's what the number is. So the absolute error comes after the last significant digit, so it's there, a 5, and then 1, 2, 3, 4, 5, 6, 7, 8 zeros. 5, 6, 7, 8. So the relative error is 5 with 8 zeros divided by 409 with 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then multiply by 100 to make it a percent. And it's 0.12%. Okay, is that reasonable? 3 significant, 3 significant, 3 significant. They should all be about the same size number. Last one, 4 1/4. That's 4.25. Okay, well that's got 3 digits. Its error would be 0.005. And so we'd go 0.005 divided by 4.25 times 100, and that's 0.12% error. 3 significant digits, still roughly the same size. Okay. Which number in the different parts of the problem above is implying the most precision? That would be the least percentage error, which is this one, 6.0100. Explain why for each. I guess that's a little unclear. Why is this one? Because it's got the smallest percent error compared to all of them. Okay. Simplify using the rules discussed to show the correct number of significant digits. When you're adding, this one's got error in this is the ones, this is the tenths, this is the hundredths. It's got error in the hundredths, so we've got to round off to the tenths. You go to the only as far as the farthest anyone goes. So you do all of it, 2.5 plus 0.46, and you get this, but you round to the tenths, the one with the least number of decimal places, or least number of significant, least number places in the decimal value. So I would have to take the 2.96 and round to this place. That would change this to go up by 1, so we'd have to write 3, and we'd have to keep the 0 to say that that comes out to be 3.0 to that place, to the tenths place, to the tenths place. Here we're subtracting. This one to the tenths, hundredths, thousandths. This one only goes to the tenths, so we have to give our answer to the tenths. 7.025 minus 1.2, but we keep it only to the tenths place, the least place that we have. So we go to the 8. The next one is not more than 5, so we leave it 5.8. Adding again. Well, this got pennies, but this doesn't, and this is, this one's to the nearest 1,000. That's the last significant digit. So we have 7,000 plus 43 plus 650.41. You'd think you would write all that, but nope. This one is plus or minus 500. So we have to round to the thousandths place because these are not measured. They're not significant digits. Round this to the nearest 1,000. That would be 8,000. 7,000 plus that little bit plus that amount would come out to be closer to 8,000 than 7,000. That's what we're saying. Speed went, if it went 50 miles per hour for 2.25 hours. 50 miles per hour, how many significant digits? 1. 2.25 hours, that's times 2.25. 3 significant digits, 1 significant digit. When you're multiplying, you go by the least number of significant digits, 1. So we'll actually do the multiplication, 50 times 2.25. We get 112.50. 112.5 miles, or, excuse me, speed. So it's miles divided by hours. So we want to divide miles per hour. So we want to go, did that one backwards. 50 divided by 2.25. And we get a speed of 22.2222, but we don't keep them all. We have 1 significant digit here. We have 3 here. We go by the least. So that's 1. So we have to round to 1 significant digit. That means skip all that stuff, and 1 significant would be 20 miles per hour. Not 22, because that would be 2. This only has 1. Okay. Area. So we do length times width. So we got 12 times 22. 2 significant digits. 2 significant digits. When you multiply, you go by the least. Well, we did give our answer in 2 significant digits. What is 12 times 22? 264, but we do 2 significant digits, so we would do this and round this down, so we would write 260 square feet. For 9E above, give the smallest and largest error implied by the measurements. Okay, so this is 12 plus or minus a half. So the smallest it could be is 11.5. The largest it could be is 12.5. 22 feet. The smallest it could be 21.5 to round off to be 22. The largest it could be is 22.5. So this would be the largest possible area. And this would give you the smallest possible area. 11.5 times 21.5 for the smallest. And then we should be rounding to 2 digits, so that would be 250. But I'll just write 247.25. But really, we should round it to 250. What's the biggest? 12.5 times 22.5, 281.25. But we should be doing two significant digits, so that would round it off to 280. So the actual should be somewhere between 250 and 280. Okay? Square feet. Okay, last page. Health diagnosis test. That an illness is gets the illness correct 97% of the time when the patients have the illness. It also says that 5% of those that don't have it, of those that don't have the illness, actually do. So consider a population of 10,000 people where 300 have the illness. So I'm going to make a table like we did in 3E. Let's say they don't have the illness, not ill, and ill. And then we have totals. The total number of people is 10,000. 300 have the illness. So how many do not have the illness? Well, 300 from 10,000 is 9,700. That clear? Okay. And they test positive, test negative. Test positive means they have it. Test negative means the test says they don't have it. The health test diagnoses diagnoses the illness 97% of the time when the patients have the illness. So if they have the illness, it gets 97% correct. So 97%, 300 have the illness, so 97% it gets correct. 300 times 0.97 is 291. Have the illness and it tests correctly, 291. That means there's 9 that of the 300 that have the illness that it doesn't catch. It also says that 5% of those that don't have the illness, 5% of these do. So it says that 5% of the people that don't have it, it tests that they do have it. Well, so they test positive even though they don't have the illness. So 5% of that. So we go 0.05 times all the people that don't have the illness, 9,700. The test says that 485 of them test positive for it. It says they do have it, but they don't. But it says it does. So the rest of the 9,700 test the other way, or 95% times 9,700, which is 9,215, or I could have just subtracted those from those and got that. So there we go. So how many people actually tested positive? Let's figure that out. That's 6. That's 17. Carry the 1. 776 tested positive. 9,224 came up with a negative test, and these two should add up to the 10,000. Make a table showing the number of correctly diagnosed people and the number of incorrectly diagnosed people. Be sure to show the false positives and false negatives. Don't have it, that's correctly diagnosed. That's correctly diagnosed. This is a false positive. They test positively for the illness, but they don't have it. This is a false negative. It says they do have it, but it says they don't. False negative and false positive. Correct and correct. What is the chance of a person getting a positive diagnosis? So that's 776. And not having the illness, 485. Times 100 to get a percent. 485 divided by 776 times 100, 62.5%. Getting a positive diagnosis, so that's a false positive. 62.5%, almost a third, 2/3 of the people will get a positive test and not have it. False positive. What is the chance that a person gets a false negative? That is, they have the illness. How many have the illness? 300. But test didn't show it. Test didn't show it. They have the illness, but the test came out negative, saying, no, 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 you don't have it. It would be this. 9 divided by 300 times 100 to make it a percent is a 3% chance that 3 out of every 100 people that have the illness won't get counted. Okay. 2 drugs, A and B, are tested on total of 2,000 patients, 100 men and 100 women, or 1,000 men and 1,000 women. The table shows the results. Give numerical evidence that drug A is better. Okay. Drug A is better. It doesn't look like it, does it? Only 5 out of 100, and here's 100 out of 900, so it looks like A is not better there. How about here? 400 out of 800, and 196 out of 200. Let's look at the overall averages. So drug A for men and women combined, so that's 405 out of 900 are cured. So what percent is that? 405 divided by 900 times 100 to get a percent. 45%. Drug A cured 45% on average. Let's do B. 101 plus 196, that's 297 out of, let's see, 900 plus 200, that's 1,100 times 100 to make them percents. So that comes out to be 297 divided by 1100 times 100. Drug B cured 27% on average. Now, what were the percentages over here? Let's just figure that out. 5 out of 100 is 5%. That's easy. 400 out of 800, that's 50%. That's easy. 101 out of 900. 101 divided by 900 times 100. That's 11%. And 196 divided by 200 times 100 is 98%. So drug A is worse for women than B. Drug A is worse for men than B. But overall, men and women combined, drug A is better than B. Again, that's because drug A worked on more people at a higher rate than it did at the lower rate, whereas B worked on a high rate for far fewer and really low percent for a lot more. So its overall average will be closer to this, and this one, since there's more people here, will be the overall average will be closer to this. It was. And this one, closer to here, it was. So that's the overall average. You got to look at the average. That drug B is better. That's right here. B is better for both women and men. And which is better and why? Well, that could be argued. But generally, we might go with the overall average. Unless it's really gender biased, then we'd say B is better for women. A is better for men, or B is better for men alone. But if you're just doing the general population, it looks like A is the better one overall. So you can make that kind of statement. Do the arguments there. Understand what's going on. Dietary supplement claims that a person lost 30 pounds in 2 months. The person pictured appears to be 250 pounds before, and I don't know what happened to the picture. Okay, what is the relative loss? Let's assume that we're seeing somebody that's 250 pounds. So what's the relative loss? So the absolute loss is 30 pounds. So the relative loss would be 30, a negative 30 over 250 times 100 to make it a percent. So 30 divided by 250 times 100, 12%. Loss of 12%. Suppose an overweight 175-pound person thought that this meant they would lose the same amount. So they would lose 30 minus 30, or the same amount on 175 times 100. So they would be losing what percentage? 30 divided by 175 times 100 is 17%. That would be their relative weight loss. If the 175-pound person lost relatively the same as the 250, so lost 12%, how much would they lose? That would be 175 times 12% loss. 0.12 is 12% in decimal, so they lose 21 pounds. So if they lose the relative amount, they lose 21. If they lose the same absolute amount, that would be 30 pounds. It's probably more likely that you lose the relative than the absolute. That's the point of that one. And the last one, you drive 50 miles at 40 miles per hour, and then 30 miles at 60 miles per hour. What's your average speed? Okay, once again, it's how much time you spend at each that counts. So the total distance you went is 50 miles plus 30 miles. So that's 80 miles divided by how long it took you to do it. So how long does it take you to go 50 miles at 40 miles an hour? Well, if it was at 50 miles an hour, it would take you an hour. At 40, it would take you longer. It's 50 divided by 40, 50 miles divided by miles per hour. The miles cancel. Miles per hour, that would go up there. And so you get 5 divided by 4 hours, 1.25 hours. 1.25 hours plus how long did it take you go the last part? 30 miles at 60 miles per hour. That's going to take you a half an hour. Or you can do it 30 miles divided by 60 miles an hour is 0.5 hours. So it's going to take you 1.75 hours to go the 80 miles. So you have 80 miles divided by the time of 1.25 plus 0.5 hours, close parenthesis, you're going an average speed of 45.7 miles per hour. You take the total distance you went, 50 plus 30, divided by the total time. The time it takes you to go 50 miles at 40 miles an hour is 50 divided by 40. The time it takes you to go 60 miles at 30 miles per hour, which can go up here, miles cancel, and you get 30 miles at 60 miles per hour, you get 0.5 hours. This is hours, and this is hours, and so you get miles per hour.